Hello, everyone, and welcome to the webinar today. I am Rhonda Geet, Director of Marketing Communications at Shapeways, and we are hosting a webinar with EOS today. A couple of things before we get started. The chat is on your right-hand side of your screen. Please enter any questions that you have throughout the presentation. And we will also be doing polls, which you will see next to the chat button. With that, I am going to turn it over to our two speakers, Carrie and Steve. Carrie is from EOS and Steve is with Shapeways, and I'm going to let them do a more thorough introduction of themselves, better than I ever could. So with that, Steve, I will turn it over to you.
Hi, thanks, Rhonda. Yeah, Steve, Director of Customer Success here. So deal with anything related to customers here at Shapeways. Been with the additive industry for quite a couple of years, and really just interested in learning about EOS today, being one of our top actual manufacturing tools that we use here at Shapeways. And with that, kick it over to Carrie.
Sure, thank you both. As Rhonda said, my name is Carrie Bauer. Essentially, my job here at EOS is to help develop our polymer technology and to help deliver it to our customers in a way that we're working specifically towards new applications. And so I manage the application development team here. And essentially what that means is I work directly with our customers to understand what are the needs of your applications, what is the pull for additive manufacturing on the end use customer end. And it's my job to help drive our technology in that direction and to help enable those new applications via working together with you. So with that, why don't I go ahead and move into the content? So I think for Rhonda, do you want to introduce this poll question?
Yes, so we have our first poll question. We just wanted to see how many people have been in the industry for how long. So if you can take a moment to fill out your poll question.
This one's always interesting. Because you would think, you know, being in the additive space, it's always like going to be way more advanced, but it's always exciting to see how many people who are also just getting into it that come to these webinars as well.
For me, it's always exciting to see that because that's just more opportunities, right? That's more people starting to see and feel the value of additive and looking for you know, people like us to help connect and to help drive that with you. So it's exciting.
Okay, it looks like we have just over 82% of the audience answering, which is great. We have a very active audience today, and it looks like it's a good mix. So with that, I think we can jump into the presentation.
Okay, great. So why don't I just start with introducing really broadly who EOS is. And so we're an industrial metal and polymer 3D printing company. All of our technology is powder-based, both on the metal and polymer side. We powderize our materials, and what our machines do is we layer by layer deposit our materials and melt or sinter via laser deposition. We have roughly 4,000 systems in the market globally. We've been a company for over 30 years, and we're roughly around 1,300 to 1,400 employees worldwide. Another thing I wanted to introduce to you today is our applications team, which is referred to as the Additive Minds team. Essentially, what our team called the Additive Minds is tasked with is understanding our customers and our partners where they're at with the additive manufacturing technology and where we can apply this technology to make a difference in your business. And so our team, referred to as the Additive Minds, is essentially focused on helping you to find your applications, develop these applications into something that fits in with your product portfolio or creates business value in some way, and ramping up production and helping you to certify that production. And what this really means is often we work directly with you to understand your needs, helping to develop a tailored solution with our technology for your products, and helping to many times connect you with manufacturing sites such as Shapeways to help you understand how to transfer that into a manufacturing opportunity and a business opportunity. And so we have a team purely dedicated to understanding your needs, taking our technology and helping to apply that to walk through the entire process from conception to reality. Just a really high level slide here. I wanted to walk through. Oh, I'm sorry. Doesn't seem to have the animations here, but I wanted to take just a 1/2 step back and introduce what laser sintering really is. And what this is, and pardon not having the walkthrough here, but essentially we recoat one layer at a time, roughly 100 to 120 micron layers. And we will deposit a layer of powder. For a polymer technology, this powder is heated because all polymers have melt points. Or all thermoplastics have melt points, and we heat the powder bed to just be below this melt point, and we use a laser, directed laser in select areas to melt this polymer selectively and to create the geometries we want. So essentially, we print in a two-dimensional method, but we do that in consecutive layers in a sense that we are building up a three-dimensional object. And so that's really how the technology works. And what this really does in terms of creating value is it allows you to take a digital file and it allows you to then implement this in a way that you have a huge design freedom toolbox. And so you can take really most parts that are digital and used in either a different manufacturing way or designed specifically for additive. And you just have a lot of design freedom, which I think I'll dive into a little bit more in the following slides.
What are some advantages of 3D printing?
So Carrie, while people are answering this poll real quick, just to kind of recap, SLS, you're taking a laser and melting that specific portion of that, image or 3D file you're trying to create, and that's going layer by layer. And if I'm correct, like micron is like almost like the length of a human hair. Would that be a good comparison to kind of figure out what you're creating?
Yeah, I think that's actually about right. Yeah, so we're creating very, very fine layers. So essentially, most builds have in the thousands of layers, and we're able to build these very fine featured detail parts. And for the most part, we use largely fairly common engineering plastics that tend to translate well to applications that are already out there and maybe being used in via other methods right now, such as molding or machining.
Interesting.
So it looks like we have a good amount of answers. And I tried to make it easy, but it does look like we have a few people with different ideas of the advantages of 3D printing. So Carrie, do you want to dive into some of those?
Sure. So what I wanted to do with this slide is just give a very basic overview of some of the areas that people look to when they're looking to transfer their product or to develop a product in 3D printing. So as I mentioned, just a almost infinite design freedom with how you're designing your parts. As you see this kind of complex bracketing structure there in that picture there, this is something that if you can imagine trying to make this any other way, it's really difficult to conceptualize that. But potentially you could make this part via machining. You're going to lose a lot of material, a lot of time, a lot of tolerances and things like that. But it's a really good way to look at, hey, we can lightweight parts that used to need to be very bulky because we couldn't make custom lattices and things like that we can now. And we can take those and we can reduce the mass dramatically, and we can reduce the material inputs dramatically. Along the same lines, functional integration. So now we're looking at, okay, there's parts that we used to have to take and machine or mold separately and assemble via different processes that all require time, all require cost, and all lead to product variation and things. Well, how can we now, given our design freedom, how can we look at this a different way? And how can we start designing some of these components to be fitting in with each other during the print and reducing those amount of input parts that are going together. In the same ways, you can, as I mentioned, a lot of customization, a lot of user-specific customization. So one of the, I think, hot areas for us now is taking a user profile of some sort, and I'll touch on this a little later, and printing specifically for that user. And finally, I think this has been a hot word for probably 20 years, 30 years in additive. It's just rapid prototyping. So being able to, on an early phase of your product, dipping your toe in the water in the sense that you can build these geometries up front, find out product failure, product improvements that need to go into your design process, and integrate those at an earlier step. Really, oh, I'm sorry, I jumped a slide, I think. Really speeding up your new product integration steps. So the way I kind of have this discussion today broken up is into a couple different areas, and I'm largely just going to touch on applications in each of these areas, because I think that's the easiest way to talk about the technologies through applications, right? So if you look at the bottom left quadrant, one area I'm going to talk a little bit about is new product introduction, and how this technology is being used to redefine how products are being developed. The second, at the top left here, is how these products, or how laser sintering is being used to consolidate products, and what that really is doing for companies and their business. And three is how can laser sintering be used to distribute your manufacturing, to digitize your product portfolio, which ultimately leads to a lot of spare part reduction and a lot of faster turnaround times for manufacturing. And the fourth one here is mass customization. So we have several, I think, really cool applications out there right now that people are starting to say, okay, how do we make our business more tuned to our users? How do we distribute this in a way that we're getting real feedback about what our users are, their shapes, their size, their needs, and printing those and building those on demand for those users?
We have another poll question. For this one, we wanted to see what applications surprised you the most that came out of 3D printing?
Yeah. Making a case for additive, I don't think people also realize just how long it takes to make a typical mold, injection molding. You know, like I know when I first found out, I was like, wait, we're talking months, not weeks. So, and then add in transportation, logistics, and everything else, especially in our brave new world. Additive just making more and more sense. Then throw in the whole factor of, you know, trying to be good for the earth, right? You're starting to see a lot of bit of focus on, you know, reduce the fossil fuels and everything else. So if we can make something locally, really changes the game, not only from a time, but also an ecological sense.
Right, and not even from just a cost and time perspective, but once you get that mold back after a month or two, then comes the hard part of looking at how well it's functioning, right? And so all of those lead times and those product improvements compound into, and now you're looking at a year, right, for several iterations. What you're able to do leveraging this technology is say, okay, first build didn't work. 2 days later, 1 day later, you're redesign, or you're changing your file, right? Your file input, which takes minutes, not days or years, and you know, building iteration upon iteration until you meet that product perfection that you're looking for.
So it looks like we have a good amount of answers with mascara brushes and performance racing cars leading the way. There are a couple others, including living cells and model railroads, that were added to the chat. So Carrie, what are some applications?
Sure. Well, why don't I step into this now a bit? So essentially what I'm going to do, like I mentioned, is if you look at the left column here, there's 4 different areas I wanted to highlight today. And all of these areas really have verticals and parallels in each of these: aerospace, auto, you know, personalization, medical equipment, things like that. But I'm just going to touch over a couple applications. So some are focused on short run production, some are consolidation of parts, and so on. So the first one I wanted to go into is just a kind of interesting example of a short to mid volume production run. So we teamed up with Rolls-Royce on a number of parts. You can see a little snippet in the top right of this picture here. Most of them were venting structures. Most of them were you know, things that you can make via machining or molding, but it's high input cost. And also this was for essentially for a platform car that they knew they weren't going to be making for 10 or 15 years. They said, okay, we maybe need about 50,000 of these pieces. You know, 25 to 75,000. We're not exactly sure, because some of these once they're on the market, we don't know the failure rates of these cars and things like that. So they had a little bit of an unknown of ultimately how many components they're going to need. But up front, they knew they had, kind of an estimate. This was a short run of production. So we worked directly with them to basically identify the costs of making this traditionally, which has, like we were talking about before, all of those input costs of molding, of machining, creating all of those supply chains. And what we found is we were able to identify 12 components just purely based on the business case alone, and the speed to market of designing and building these, that essentially saved them about 10 to 20% up front of being able to build these and use them for their limited time automobile there. I want to also touch a little bit about how people are looking at this technology from a consolidation standpoint. So this is a case study we partnered with a customer on, where they were making a gripper. So this is part of an assembly line where this is essentially what this does is there's a unique profile to this gripper to where it's able to pick up parts throughout the process and move them to a different, essentially to a different manufacturing line and things like that. So it has to have a really defined seal and have a good hold on basically what it's trying to do. So this is really the fastener and the basically the hydraulic section of it, and then there's grippers on these also. So a lot of components went into this traditionally, how they were doing this before, largely because all of the piping and the air handling had to be separate from the gripper structure. So these, there were connectors, there were tubes, there were little spindles, things like that. Well, we were able to redesign with them and work that down to actually 3 different parts. And the reason we were able to do that is all of these functions that they had to look in separately through hoses, through connectors, things like that, we were able to build into one solid structure. And this doesn't include the grippers, but this is essentially the functional component of moving air, holding the grippers and things like holding the actual, the rubber gripper parts. And so what we saw is we were able to reduce the weight dramatically, which led to a reduction in cost, because this is all, a fraction of the material required to make the original part, a fraction of the time, a fraction of the, the lead time and such. And so that's kind of I think a cool example of, hey, it's not always just a straightforward, let's just, look at one, either material or lead time or something. You can actually make a real difference in how many components you're using to make a functional part work, if you're open and willing to look at redesigning that. This is a bit more of a broad example, but same things are happening in the impeller space, and other, there's heat exchangers, things like that traditionally require a lot of different components coming together. And this is just an example with a partner that we were able to reduce a 73 component impeller down to 1 component. And the production speed of that just improved dramatically, as well as the quality. The reduction in failure rates also went up really high, because if you think about, especially on small parts, if you're taking 73 components, they all have their own tolerance, right? And imagine putting all of those tolerance parts together. You have a lot of rejections, you have a lot of failures of those parts, but being able to integrate that into one structure really brings a lot of functional and cost advantages. Those are 2 examples. There's some broad other areas that this is really, active for people looking at and integrating into their business now for cost savings, for lightweighting, things like that. Example on the left here is actually taking a generative design and replacing what's traditionally a metal component armrest for an airplane with a structured polymer material, that you're able to reduce a lot of the mass, because you can make these lattice structures that are specific to keeping that surface strength up on this part. And so this was one that we did with one of our aerospace customers, and saw, a really large dramatic reduction in weight, which is really important, right? Because they're under pressure all of the time to improve their fuel efficiency, to improve the business case and the environmental case at the same time. And so they're looking to us to help drive some of these metal replacements, some of these lightweighting opportunities. Same thing with being able to print, bearing structures really, creatively. And also this, if you look at this venting structure, try to imagine making that any other way. This is a real venting structure that is meandering through this part in a way that it can accomplish its venting plus fitting into a really tight space at the same time. This was a custom structure for an application that we worked on.
The first one is for the automotive parts.
Sure.
How many were made and how well engineered was it compared to traditional manufacturing methods?
Yeah, that's a good question. So roughly 50,000 were made. So in the ballpark of what they expected, they did make. When you say well engineered, there is some complexity to working with. Let's use the automotive example. That's all a very highly regulated industry, and they're always driven by specifications and things. And so it is part of the consideration when you're going, especially if it's a company's first product going into this area. You have to understand for each part the performance specifications so that you can translate that into a viable part. In this case, for this specific example, those were not structural components to the automotive, to the car. Plus, they also weren't under the hood parts, so that actually reduced the performance specifications that were needed for that. So we just really had to deal with the requirements for venting structure, casings, and things like that, which can also be tough, but they're not the same level as something as sitting next to the engine in the front. And so there is a innate difference in most laser sintering polymers from what you will see in the industry, and all of that needs to be taken in consideration when choosing your material and your machine.
About materials,
your application.
EOS has several different plastic materials and others. Are you thinking of expanding into precious metals or other materials, and what do you find to be your most popular?
Yeah, so largely this talk is focused on our polymer portfolio. We are, looking into and working on quite a few of those topics on the metal side also. So there's some precious metal work going on and things like that. On the polymer side, I can answer from my perspective is I continue to see the, a couple really high growth areas on our materials. One is our customers ultimately, want a product that is environmentally friendly, but also efficient from a cost standpoint. And so we're continuing to work on our materials to make them higher recyclability and lower waste. And so we're working on several products right now that will help us, drive a more efficient product and drive a more efficient product from an environmental plus a business standpoint. Additionally, I think there's a lot of really cool work and opportunities in the composite space right now, because as we dig deeper into aerospace and automotive, additive manufacturing is getting further into working our way into the specifications, which gives us more opportunities to design materials specific to auto and aero and other applications out there that demand new materials.
Shocked by how you could take 78 parts and bring it down to one when we were talking about the slide back there. And I think that really just goes into showing how some of the limitations of creating molds with complex geometries are going to continue to show why additive is catching up or will actually surpass traditional manufacturing with a lot of more of these complex parts, which actually is kind of a perfect segue into these custom shin guards.
Right. Yeah, absolutely. So, so the next thing I wanted to kind of talk about is more of a user-designed approach it's kind of a mass customization approach to delivering a truly customized product to the end user. And so, one example that we've collaborated with several companies on is, okay, here's a shin guard. We understand how to take, and it's very, many people understand how to take a scan of a shin, right? But currently, really what's being done there is if a company does take a scan of a shin, they essentially mold a part that's used for that shin, and they're applying general foam to that and trying, the best you can to mold parts to someone's specific profile. What we did is we worked to take, you know, a bit of a more compliant nylon, which is nylon 11, and create a unique lattice structure that's able to absorb a lot of the typical impacts you'll get from soccer balls, from other people's feet. The reason you're wearing a shin guard in the first place is you take a lot of errant kicks and things like that. And so we designed a lattice that was specifically aimed at taking the abuse that you see and you need to you know, guard against with a shin guard. And so what we were able to see is we were able to improve the breathability of the shin guard. So if you imagine, you know, most of us have worn these kind of clunky, as kids, this clunky safety equipment, things like that. You instantly sweat and itch if you're like me. You know, this particular case was really cool because you're allowing air to pass through here. You're allowing, you know, much better breathability, much lighter weight. It just feels more natural, while we were able to achieve the same and higher, actually, response to damage and response to, you know, impact. And it's really cool because you can customize this based on a scan, which means it truly is user designed. I'm going to stick kind of on this theme for a while because it's a really active area for us. Another effort that we have ongoing is we work with a company called Hexer. Hexer is a leader in specialized helmets for bikers, specifically for bikers, largely. And they have a, you know, they essentially had a problem statement of, okay, our customers want helmets that fit better, helmets that perform better, and you know, they're demanding that these are more, you know, tailored to what their profile is. And so we worked with Hexer to develop a process that takes a 250,000 scans of your head. So you put on this helmet that's pictured in the left, this head mat thing, and it takes all of these data points. And essentially what that does is it creates the shape of the part, right? The shape of what the helmet needs to be, especially the inside shape that's going to ultimately be against your head. Because when you're talking about impact, having a snug fit really does make a big difference. And what we then worked with them towards is taking this, translating this into an open cell structure, as you see there, that accentuates the material strength in the direction of the impacts that you will be, you know, potentially receiving, while again offering a lightweight structure that allows better airflow, lighter weight, so less, you know, less weight on your neck and head while you're riding. We're able to dye it, and then they're actually able to customize it too. So ultimately, you know, if a person wants to put their name on it in case it gets lost, they want to put, you know, personalization on that. All of that is achievable via this process, and this is one way that laser sintering is being leveraged to truly, you know, distribute mass customization to customers that
I was going
want
to say,
user
it's
profiles.
fascinating. The past two examples you gave, both the shin guard and the helmet,
Go ahead.
it seems like the lattice structure is almost imitating nature when you talk about the cell structure, you know, like in creating more customized and advanced ways of protecting ourselves, while, you know, at the same time being able to specifically make it just for one person. Pretty amazing technology.
It's funny, if you know, you do find that somehow nature has found the strongest structures, the most efficient structures in many ways, right? And so I think you're right, from a cell strength standpoint, a lot of designs lead to something that is found in nature that is meant to accomplish a similar purpose, right? Back to one more automotive example I wanted to give. We worked with Mini Cooper, and essentially this is a true personalization, mass customization example, is where folks could not only print a dashboard insert that is according to what they're choosing on the Mini Cooper website, but they're able to choose the color. They're able to actually put their names in it. So your car actually has, you know, your customization in it, which is, I think, really cool. And something that I think people have been asking for quite some time. So I think this is one more example I wanted to give. And this is really on the orthotic side of this. Is so we work with a company called Atrex that is a leader in making custom insoles for their customers, which, you know, many of them have back pain, many of them have foot pain, things like that. And essentially the way this is traditionally done is they take a foot scan and they custom shape these parts and things out of some foam and things like that to make unique profiles. What we realized we can do with them is we can take one of our soft materials and we can actually create lattice structures that change the response of our materials on the user's foot. So essentially what they're doing is they're taking a scan. I think I can go to this in the next slide here. They're taking a scan of the user's foot on the left here, and we translate this with them to a specific material density and a specific unit cell shape, which in translation gives a specific pressure response back to the user's foot. So all of this essentially is customers can go into their store, scan their feet, and within a number of days, they can have an insole that's truly designed for their weight and mass profile, which we've seen is really helping customers out and improving their pains and also their balance and their, you know, just their livelihoods, especially for people that are on their feet a lot. And it's reduced for Atrex, it's reduced a lot of the input times, the waste, the costs that have went into the traditional time, and allowed them to have these fast turnaround times and fast custom turnaround times, and that have really accelerated the ability of people to get custom solutions. Another example of this on the eyewear side is there's a company we've worked with called Fitzframes that found, you know, they had, each of the founders here had children, and they realized, man, we're buying new glasses every single, you know, year, if not earlier, for our children. It's a major pain point of waste, of rework, things like that. And so what they said is, we want to create a seamless way for kids to pick their own eyeglasses, to get, you know, to choose that customization, and us to deliver them really quickly. So what they have is essentially a subscription-based model. They're running EOS machines, and they've created an app where a child can essentially look at his or her own face, scroll through a number of glasses, pick their color, pick their size, pick their style. It goes straight to the printers. They get printed, dyed, and fit for lenses all within a few days and are at their door. And so they can avoid a lot of the traditional processes that needs to go in there. And since it's a subscription-based model, and children can, you know, basically swap out glasses as their face changes, as their needs change, and things like that. And so it's another example of how we're revolutionizing the mass customization market with our customers. And one final one, I think, would be just taking it to the medical segment of custom orthoses with, you know, with some of our partners here that are actually printing the entire orthotic for users that have real medical needs too. And this essentially what this has been able to accomplish is very similar things. Is weight's a real problem on orthotics. So carrying around a really heavy orthotic is also often, while it helps, it also hurts from a balance standpoint, a mobility standpoint. By being able to create these open structures and these user design structures, we're enabling a much faster recovery time, a much more user-focused production method that's really generating, you know, medical devices that are tailored for our customers. And then the last application I wanted to just touch on quickly is the concept of spare parts and inventory. So from a business case standpoint, especially from products that have been in the market for a while, one pain point many companies have is, how do we manage our spare parts for these machines or equipment that's in the field? Essentially, the way they manage that is just by having piles of it in warehouses often, because it's really difficult to project how many parts will be needed. And if you're under on that, then you really have a pain with your, you really have an issue with your customers and with your lead times. And so it's really common in the industry for folks to be burning a lot of their internal capital on having these large inventories. Well, if you think about the ability to take a digital file have what's referred to as a digital twin for these parts, keep that on file. You can then just have a number of machines on standby and ready to print on demand these parts that customers are requiring to keep their equipment up and running. And so what we're seeing really is there really is a very strong business case for converting as many of these aging parts or parts that will be your, your replaceable parts for new products, and converting those to digital files so that you can have those, when needed, without having these massive warehouses full of aging parts and inventories that are just sitting in warehouses. So we've worked with a lot of customers to look through their product portfolio. This is another thing that Additive Minds works on, is looking through your product portfolio and saying, okay, which ones of these could work in an additive process while retaining the performance specifications you need, and converting those to digital tools so that they can be done, so they can be printed on demand. And one company that we have done this with successfully is Daimler, who has makes something called they have a company called EvoBus. And we went through all of their components. We identified over 380, and we essentially were able to digitally convert these to where their inventory has went way down, while they're still able to meet the same needs of keeping their fleet up and running and keeping their customers moving as needed. And there's a little snippet of some of the parts we designed with them. Some of these are designed to also mimic leather interiors and things like that, so that it's a seamless replacement of the original parts. So that really, from a high level, is some of the applications I wanted to deep dive on. What I wanted to do, and as we get towards the end of the talk here, is just to go a little bit into the material side of things and how EOS manages our materials and our products. And I just want to give a high level overview of that. In general, EOS has 14 plastic materials that we currently offer on our printers. Shapeways runs many of these materials. And we also have a subset of EOS that is a company called ALM, Advanced Laser Materials, that is more towards customization of materials for specific applications. And so we have EOS, which rolls out standard materials, and we have ALM, which works directly with our customers to say, okay, you have a specific ductwork in a aircraft that has, that needs to be ESD, needs to be tolerant of these things. Well, we then often take on that as a potential custom development project. So we have the ability, to support our platform materials while developing custom materials also. And so just a list of all, and you can find these obviously on our website, a list of our materials. A lot of these are nylon based, like I've been discussing. Nylon 12 is our highest volume material on the market right now, and Nylon 11 also is a very popular material for applications that require, I think, more dynamic mechanical strain and more compliance in a little bit in some ways. We also have materials that are carbon fiber filled, aluminum filled, which improves the ability to dissipate heat. So some of the short run production molding applications uses aluminum filled materials. We also have a number of elastomers. So we have TPUs and TPEs that we've employed. The insole application that I discussed a couple slides ago is actually using a soft material, and that was able to create that kind of custom soft feel that the users needed. And we take very seriously managing the quality of our powders. So we have suppliers that comply to our quality standards. We do our own quality checks before we send, and our quality checks include mechanical testing in our printers before we send any material to our customers. So these are all, have certificates backing them, and all of the powder is managed quality-wise at EOS through building and running witness coupons and maintaining a quality powder process. So just to go back to our ability to create custom materials through Advanced Laser Materials, which is a subset, like I said, of EOS, what we really do here is we're able to take, example, traditional Nylon 11, Nylon 12, and I'll give a broad example. An automotive customer may say, okay, we need something that is a really high heat deflection temperature. Has a higher heat deflection temperature. It needs to be flame retardant because it's going to be in a really hot environment. And it needs to be, able to withstand some of these dynamic mechanical strains that it's going to undergo. So we will then go to our portfolio of polymer materials, and we have a large range of fill materials that we're able to look to, such as glass fibers, mineral fibers, carbon fibers, things that can allow us to make materials conductive or ESD, and we essentially use that toolbox to develop a custom material if the business case and the application is asking for that. So a large part of our business is helping to identify the needs of our customers specific to an application. If we don't have a current material that meets that, we often can make it. And often we'll help enable our customers by working with Shapeways to then say, okay, we have a material, we have a production process. Shapeways can help fill that production need with our material, and we can then have I think, cradle to grave solution in terms of conception to specified material and process to a production platform, right? There's three, I'm near the end of my presentation. There's three materials that I just wanted to highlight that we've developed with customers for applications. So one is FR106. This is a material we actually developed with an aerospace OEM that is currently on many aircraft, actually as ductwork on many aircraft. This is a nylon 11 material that has flame retardant additives in there, which makes it compliant with a lot of the FAA regulations for flame retardants, so that we were able to take a need that they gave us and create a custom material that is now actually on aircraft, on many of the aircraft that are in the skies right now. And these are used not just for ductwork, but they're used for some casings and some air vent structures within an airplane. It's even being used in some automotive interiors, which have somewhat similar flame retardant requirements in cabin applications. There's another one I wanted to highlight. It's a high performance nylon 11 with carbon filled structures, which is specifically designed to resist impact and to reduce fracture. And this material actually has very high isotropic properties, which means in the X and Y, it also is very similar in the Z direction property-wise. So that is something within 3D printing that is a common challenge. In your print direction, your properties can often be different than outside of your print direction. This material was designed to combat that in a way that gives you very uniform properties. And this is used in a lot of racing applications, a lot of custom cars, and also regular commercial cars. It has a couple of applications in there also. And I think the final material I wanted to just give an example of something that we've done in the past is we've taken a nylon 12 and we've added glass-filled beads, basically glass beads, into the structure and some other additives to basically result in a very lightweight structure that retains stiffness and strength. And so if you go back in the presentation, I was talking about lightweighting out structures, replacing metal, replacing current components to really improve efficiency and weight. Well, this is one of those materials that is doing that by really creating a reduction in mass while retaining weight. And so we have this. This is being used in drone applications, in bike applications, and again, in different sports-related applications that require lightweight structures. So with that, I wanted to wrap up, and I appreciate your time and attention. What I really wanted to say is we at EOS have the ability to take you from, conceptualizing a new product, looking at your business case, walking you through that process. And with strong partners like Shapeways, we're not just able to, sell you a material or a machine. We're able to help you develop that process and really turn that into a supported production scenario with Shapeways to meet your production needs. So
yeah, one of the applications you talked about, actually, Fitzframes. I love that story just because it was one of those interesting stories of how a customer kind of started off identifying what their problem was, what they wanted to figure out while creating the glasses for children, actually worked with Shapeways for all the early stage prototyping and really kind of conceptually building out the business, to then eventually, once they ramped up and had the business going, coming over to EOS and buying machines. So again, kind of just one of those wonderful symbiotic relationships you saw come out of this whole process.
It was a great story, because they brought all of that knowledge around what it takes really to develop a new eyewear technology. We brought a lot of that knowledge around, what the process can be done, or how the process can be tailored to accommodate those requirements. We put those together, and like you said, it really, really was a successful concept. And through Shapeways support and Additive Minds EOS support, they now have a business up and running that's doing great and meeting a real market
Thank you
need.
very much, both of you, for giving such a great informative presentation. There are a couple of questions that we didn't get to that were out of the scope of this presentation, but we will follow up with everyone if you did not get your question answered. And in the meantime, everyone have a wonderful rest of the week. Thank you.
Thank you very much.